Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks. So it's a great pleasure to introduce Karthik Padabiraman. Karthik is finishing his PhD at the University of Illinois in Urbana-Champaign under Ravi Iyer. Karthik's work has been focused on fault tolerance and, as he's going to talk about, critical data. So this is really interesting work in the context of the hardware developments, and as we see into the future, we're going to see more and more unreliable components in hardware, and so we'll see Karthik's going to talk about how we can deal with those issues as they surface up to the software. Thanks.
Thank you, Ben. Well, it's a great pleasure to be here today. Thank you all for coming to my talk. So before I launch into my talk, a little bit about me. As Ben was saying, I come from a fault tolerance and security background. But during the course of my PhD, I've applied techniques from compiler design, computer architecture, and formal methods to design these kind of fault tolerant systems. And what I'm going to be talking about today is one particular aspect of my dissertation work and the work I've done here at Microsoft on critical data protection for reliability and security. So my broad motivation is to build trustworthy systems. As you all know, trustworthy systems are those that are both reliable and secure. So if you look at the kinds of threats to building trustworthy systems, first you have software bugs, which cost the US economy $60 billion a year. Then you have hardware errors. Now most of us think of hardware as being inherently dependable, but it turns out as you shrink transistor sizes, they're becoming more and more susceptible to things like cosmic radiation and electric disturbances. So we really need to worry about these errors also. Now from the security side, security attacks are now big money. So there are organized rings out there that try to extort money from you by attacking your security network. And also we're seeing a proliferation of devices, so it's really hard to come up with a one-size-fits-all security technique. So as I was saying, my motivation is to provide protection from both errors and attacks. So if you look at the other trend in computing today, it's the notion of platforms. Now, when I think of a platform, I think of Windows or Unix. But there are also other kinds of platforms that are coming up out there. So one example is smartphones. And another example are web browsers. Now, these platforms share two common features. First is there is very little isolation among the components in these platforms for functionality purposes. And also, the economic value of the platform really derives from it being extensible. So they allow third-party code to be loaded in and supported in the same platform. So all this means that a single component can actually bring your entire platform down if it's not written correctly. So you need both fault and attack tolerance in order to ensure dependability of these platforms. So that was the big picture. Now let me zoom in on a particular class of errors and attacks that most of you will be familiar with and give a little preamble there. So I'm going to be talking in this talk about memory corruption errors and attacks. So as you all know, programs written in C++ are not memory safe. By that I mean a pointer can write to anywhere in memory. And it's a fact that many programs are still written using these languages. So to define a memory corruption, it's basically when a memory location is either modified by a pointer writing outside its bounds, which is the classic buffer overflow, or by a pointer writing to a freed object, which is your dangling pointer error. And how big of a problem are these memory errors and attacks? Well, they account for 66% of real-world security vulnerabilities, according to CERT database. And the recent study found that 55% of application crashes in the field, in fact, come from memory corruption. So You
said something different than what was on your slide back on the previous slide. You said 66% of real-world security attacks, as in events, or is it vulnerabilities that are found in software?
So that's a good point, right? So these are vulnerabilities as reported in the CERT database. So as far as I know, no one has really gone and profiled how many of these are attacked versus how many of these are not. But these are all exploited in some way, or someone has found an exploit for them. So yeah, I really meant to say vulnerabilities. Thank you for pointing that out. So let's look at existing approaches to memory corruption. So there's one school of thought that believes that rewriting in safe languages is the way to go, and rewriting code in Java or C#. And while this may in fact be the way to go for certain applications, for the vast majority of programs out there that are already written in unsafe languages, this involves a considerable investment in programmer time. And also, even if you did manage to write large portions of your software in a managed language, you're going to have performance critical components that are probably still in unsafe languages, and you need to worry about them. The other school of thought is that we can use static techniques to do away with memory corruption or memory errors. And there's been some excellent work here at Microsoft on SAL and ESP that will allow you to check your code statically before you check it in. The one major disadvantage of these techniques is that they require the entire code to be statically analyzed before you're allowed to actually deploy it, and which may not be possible if you don't have the source code available to you. And also, as most of you have worked with static analysis tools know, some of these have high rates of false positives, and we need to deal with them. Now, the other promising approach here has been in terms of runtime checking techniques, and these are what I call the all-or-nothing kind of techniques, which basically say, so you have dynamic checking, which is going to go and check every pointer right at runtime, though at least those that you couldn't remove statically. And the problem with these techniques is they can have overheads as high as 100%. And an example of this would be CRED and Secure. Now, the other sort of school of thought from MIT says that so they make the observation that many memory errors don't matter to the program. So when a memory error occurs, simply pretend as though nothing happened and continue execution. And this is the failure of oblivious computing, which actually it turns out works fine for programs like servers where the error propagation is limited. But in reality, programs do have error propagation, and in my opinion, this is a very dangerous thing to do. So in contrast to these approaches, my approach is more a data-centric approach, what I call critical data protection. And it's based on this observation that some application data in your application is more important than other data. So rather than treat all data as equal, we are going to focus on protecting this subset of data, which I call critical data. So to give you concrete examples, from a reliability point of view, let's say you have a banking application. Your bank account data is clearly more important than, say, your GUI data. Or in a computer game, your game player data may be more important than, say, the state of the game world, and so on. And similarly, from a security point of view, you can think of password variables or activity logs as being things that you would want to protect from the attacker. And what I'm going to present is a unified approach to protect this critical data selectively and make sure that it's resilient from errors and security attacks, and in the process, allow you to realize significant performance and resource benefits. So to sort of show graphically what I just said, so imagine this big yellow oval is your application data, your little green oval is the critical data. So even if the rest of the data is corrupted due to memory errors or attacks, you want to make sure that the critical data is itself safe from corruption. And one advantage of this technique is that you can actually choose the critical data and incrementally choose more data over time. So you can apply it for legacy systems and continuously tune it based on the protection required. The other major advantage here, as I will show you in the techniques, is that you only need the code that actually modifies the critical data. You do not need access to the rest of the code in your application that just writes outside this oval. So what all this really buys you in the end is that you can get local reasoning about a module's critical data independent of the other modules. So you as a developer can protect the data in your module and be certain that it's free from corruption due to other modules in your program. And this is an important goal, I believe, when you consider the trends in computing I talked about, which is the rise of emerging platforms and increases in errors and attacks. So before I launch into my exact techniques, let me give you a big picture. So I've looked at the critical data protection paradigm in the course of multiple systems I've built, both at the University of Illinois as well as Microsoft Research. So as part of my PhD thesis, I came up with two techniques, critical variable recomputation and information flow signatures, in collaboration with colleagues at Illinois. So critical variable recomputation actually deals with protecting critical data from hardware transient errors. I'm not going to be talking about that today, but if you have questions, I'd be happy to take them offline. I'm going to talk about information flow signatures, which is a technique to protect critical data from memory corruption attacks. I'm also going to be talking about Samurai and critical memory, which is work I did here at Microsoft in collaboration with Ben Zahn and Vinod Grover. And here we are going to focus on protecting from memory corruption errors. And finally, I also worked on Tolerase, which is a system for tolerating race conditions. And this was joint work with Darko Kidovsky, Ben Zahn, and Rahul Nagpal. So the other way to sort of categorize these techniques is what I've looked at in my dissertation is mostly been on error and attack detection, whereas what I've looked at here is mostly on detection as well as correction. So as I said, I'm going to talk mostly about IFS and Samurai. So before, yeah, I'm sorry. Sure.
So in your SRAM model, you basically trying to prevent errors or attacks against the application itself.
That's right.
But if I compromise the system where other vulnerability, then still your critical information, you won't protect against that.
So are you talking about like operating system rootkits and virtual machine-based rootkits?
I mean, another application has a root privilege, I can compromise that and get to own the machine.
So right now, I do not deal with those kind of attacks. But I'll come back to your question when I talk about my future work, where I'll discuss how we can address that. Thank you. All right. So in addition to the critical data protection, or rather, let me sort of give you a one-slide introduction to what my dissertation research is about, and then I'll focus on critical data. So I've been broadly involved in building efficient error and attack detectors for applications. So by this, we want to be able to detect errors and attacks before they cause problems in the system. So I built a unified compiler framework for static analysis and implemented this in software and reconfigurable hardware in collaboration with my colleagues. And this has actually been prototyped as part of a Trusted Iliac project, the Trusted Iliac project at Illinois, which aims to build reliable and secure systems using reconfigurable hardware and software. I've also worked on dynamic analysis techniques and dependability evaluation. In particular, I've looked at how to derive detectors using machine learning techniques, and I've built probabilistic models of coverage evaluation. And finally, a recent direction that I've been exploring is the use of formal techniques for verifying detectors. So I've looked at both model checking as well as theorem proving techniques. So I'm not going to be talking about these other techniques in detail, but if you have questions, I'd be happy to talk to you about them offline. So in this talk, I'm going to be talking about two techniques. I've motivated the problem and explained my approach. So the first technique I'm going to talk about is this notion of information flow signatures for security. And this is joint work with my colleagues at the University of Illinois. So the IFS technique is based on the observation that the results of memory corruption are really undefined according to the C++ language semantics. Now this is not a new observation, but what we really observe is that the runtime is not enforcing this isolation among objects, but the language semantics makes the result of memory corruption undefined. And it's precisely this that attackers exploit in violation of the language semantics to override data and application. Now, what is innovative, or what we have done here, is to selectively enforce the source level properties of writes to this critical data at runtime. So I will explain that in a minute, but there are a couple of things to point out there. So first is, since we are enforcing source level properties, we don't get false positives because they're all based on the source code. Secondly, we can ensure that the critical data's integrity is preserved even if other data is compromised by the attack. And this also allows us to get local reasoning and incremental protection, as I told you. Okay, so let me look at the class of attacks that we want to consider here. So certainly we want to consider memory corruption attacks, like buffer overflows and format strings. We also consider insider attacks, where you have parts of your code that are in and of itself malicious. So malicious libraries or third-party plugins are part of my attack model. I'm also going to consider program binary modifications after it has been through our compilation process. And the real sort of insight here is that we can enforce this information flow signatures using compiler and runtime. So at compile time, I'm going to extract the backward dependencies of critical data, of critical variables in the program, and convert it to the information flow signatures. And at runtime, I'm going to recalculate the information flow signatures based on the observed writes to the critical variables and compare the runtime signature with the derived signature. A mismatch indicates a memory corruption attack, and the program will be halted. Yes.
You come up with like the list of critical variables.
Okay, that's a good question. I will come back to that later. But for now, what we have done is we have looked at these programs and picked out variables that we think would be ripe targets for an attacker. Meaning by attacking those variables, you can actually gain control of the application in certain ways. Now, that being said, I am actually not going to talk about, okay, so I should clarify, I'm considering data-based corruption, meaning you corrupt some data and try to get control of the application. So I'm not going to talk about things like return address corruption, etc. So those are, there are techniques out there that already deal with protecting control data. What I'm focusing on is this non-control data, which is important to the application. Okay, thanks. All right. So let me give a conceptual example of the information flow signatures approach. And this is from the OpenSSH program. I just want to say that here, this example is only to illustrate the concept. This is not the way we really implement it. So here I've numbered the lines in this program. So what this function does is accepts a user password in the auth context and then the system password. And then it's going to return the value of authenticated if these passwords match. So it's going to return 1 if the passwords match. Otherwise, it's going to say the authentication failed. So here, authenticated, let's say, is a critical variable you want to protect, because if an attacker manages to somehow influence that value, then he or she could authenticate themselves wrongly to the system. So what we are going to do is to encode the entire backward dependencies of the authenticated variable in this program. And that's actually the signature that you see there. The actual encoding is not important. I'll show you how we do it. But for now, what we do is we go back across for each data dependence of the state program statement 6 and encode it in this fashion. Now, let's say there was a hypothetical format string attack at line 5 here. And for those of you who don't know, a format string attack basically allows a user-provided buffer to be used as a format string. So there are smart tricks an attacker could play to write anywhere in memory using this attack. Although this is hypothetical in the sense that SSH doesn't have this attack, actually another application we looked at, FTP, has a very similar attack in the authentication function. So it's not that hard, and it's not that hypothetical in that sense. So let's say from this format string attack, you wrote to the value of encrypted password variable, which is being used here. So you see that the observed runtime signature for the variable authenticated actually changes because of the write to the backward slice. So you see, if we had a technique to actually monitor this and compare all the writes to the authenticated variable, we would notice this mismatch in the signatures, and we could halt the program and take corrective action. So the real key here is that by encoding the entire backward slice, you can detect any memory attack that attempts to influence a critical variable, not just the one that writes directly there. And that's actually one of the key elements here, that we need to go back the whole range, because remember, we are protecting selective variables. So let me present the overall algorithm, then I'll go into details. So we first do static analysis to extract the interprocedural backward slice of critical variables. And here we identify the instructions in the backward slice as trusted instructions, and the data objects at the top of the slice as trusted data. We also identify the target data objects for these trusted instructions. All this is done at compile time. At runtime, I'm actually going to use a combination of hardware and software to enforce the backward slice of the critical data. So we break it into 2 levels of checks: level 1 check, which is implemented in hardware, and level 2 check, which is implemented in software. And we'll halt the program if either of these 2 checks is violated. So let me explain the intuition behind both of these runtime checks, then I'll explain how we actually enforce them. So as I was saying, all the instructions in the backward slice of the critical variables are labeled as trusted instructions by the compiler. So what the level 1 check is going to ensure is that only the set of trusted instructions can actually influence the value of critical variables at runtime. So that's the invariant it preserves. And you need to check this for all instructions in the program. Now remember, you may not really have control over all the third-party code that gets loaded here. So you have to really enforce this check in hardware to make sure that whenever an instruction is executed and it's going to influence the critical variable, you have to make sure that it's trusted. So if, in particular, if there's an untrusted instruction that tries to influence it, this will be prevented. Yes, you had a question?
Yeah.
I'm talking about right. So I'm focused on critical data integrity. Confidentiality is another issue that I haven't explored. Thank you. Okay. So at this point, you may be thinking, okay, we have enforced that trusted instructions write to critical variables. What else do we need to do? So we have this level 2 check, which makes sure that only each trusted instruction only influences its critical variable and no other critical variable. So it's sort of like trusting the trusted instructions, but making sure that they're doing the right thing. And what we enforce here is that each trusted instruction writes only to its allowed target objects as determined by the compiler. And the key insight here is that you only need to check this for the trusted instructions in the program. So you can actually do a much slower software check because you've done the part of filtering trusted instructions in hardware. You can actually check whether the trusted instructions writing to its critical data using software only. You had a question.
Yeah, can you comment a little bit? So I heard about this point-to analysis. It basically tell you what instruction can write to what memory location.
That's right.
And yours, you kind of mentioned both. In the traffic, in the information flow, basically need to track through, right? I can write to A, then B, read A, then write to B, right?
Right.
That's kind of the information flow. And here you are talking about is very similar to the point-to analysis. Can you compare your approach with that?
Well, so yeah, that's a good question. Thank you. So what we are really doing is we are enforcing the pointer analysis discovered properties, but for the critical data alone at runtime. So I am in fact going to use compiler-based pointer analysis to extract which writes to where on this backward dependence chain. But the novelty here is to make sure that only these things write at runtime and only for the critical data. Thank you. All right. So as I said, if a trusted instruction tries to write to a different critical variable, we will actually prevent it from doing so. Now this serves to protect two kinds of attacks. So one is if your trusted instruction somehow depends on user input. So let's say you use an array index somewhere and you're using that to write to a critical variable. Now you trust that that instruction writes to A of I, which is the array index. You don't trust that it writes to maybe a password variable. So we want to, so the compiler analysis will actually contain where the trusted instruction writes, and you want to make sure it's obeyed. The other thing it protects is, remember there are untrusted third-party modules here. So you want to make sure that trusted instructions there don't come and write to your own data here. So let me sort of walk you through the compilation process, then I'll show you how these checks are implemented at runtime. So this is a very abstract block diagram. Okay, I'm not going to go into the details. If you have questions, I'd be happy to get into that. So we start with the trusted modules and the annotations for critical data. So as a programmer, you write these annotations. Now, we have a trusted compilation path for these trusted modules that allows us to generate the object code of the trusted module and also to generate the trusted instructions and their target for this module. So the assumption I'm making here is that only the trusted module can legitimately modify critical data. No other module has any business modifying critical data. So the object code of untrusted modules can be directly linked with the object code of the trusted module to get this composite module. So notice we don't need the source code for this untrusted module. Now we use the linker. I mean, after the linker has gone through this, we go and create a final executable in which we have actually digitally signed the critical data and the trusted instructions. So the trusted compiler makes sure that the critical data and trusted instructions for this module are part of the final executable in a verifiable fashion. Now, I'm sorry about the truncation of my title there. That should have said IFS level 1 check implementation, and we implement this in hardware. So there are 3 key points here. So in hardware, we associate a special bit with every instruction and data item. So we call this the trusted bit. Now, at load time, program load time, we assume there's a trusted loader, which verifies the integrity of the trusted instructions or the data that has been signed by the compiler. And this trusted loader then goes and initializes the critical data as well as the trusted bits of the instructions or the data in the slice. So this is at starting time. So you get the initial data elements as well as the trusted instructions. Now at runtime, you will propagate the trustedness of a data operand by using the following rules. So trustedness of an instruction's destination is, or rather instruction's destination is trusted if and only if the instruction is trusted and all its operands are trusted. So some of you may notice a similarity here to taintedness, but the key difference is taintedness is going to track who is not trusted, and it's going to track where you come from, where you get user input. Whereas what trustedness is doing is saying there's a small subset of your trusted instructions, and I want to track which data and which instructions are going to be used there. And hence we can actually avoid some of the false positives issues with taintedness there. So this is the action table. There is a table of actions that need to be taken for each of these cases. I won't walk through this whole table, but I just wanted to give you the high level insight. So whenever anything untrusted writes to critical data, you should raise an alarm, okay? Because of course you don't trust it, so why is it writing there, right? Now when it's untrusted, when the instruction is untrusted and it writes to non-critical data, it's fine. You can just allow this to proceed because this is what the majority of the instructions are going to be doing. When your instruction is trusted but its operands are not trusted, and it tries to write to non-critical data, we'll raise an alarm. Because the fact that the instruction is trusted means that it's at some future point potentially going to go and likely to influence the critical data. So you want to sort of cut the propagation early on in the chain, and you raise an alarm there. If, however, both the instruction and its operands are trusted, you allow it in level 1 check. But now you pass it to the software check, which is going to make sure that the instruction is really doing what it's supposed to be doing. And that's what this is level 2 check implementation in software. So whenever you see a trusted instruction write to critical or non-critical data, you get a trap from the level 1 check. And when I say trap here, it doesn't mean like an OS level trap. It just means like a high-speed trap handler that's part of your application. And when you get this, you get the PC and the destination address. So the first thing you do is to look up the allowed target objects for this trusted program counter instruction in a special table, which we call the instruction to allowed data table. And this is initialized by the loader. Now, starting from there, we look up the address range of the allowed target objects based on object type. So there are 3 kinds of objects we consider: local variables, which have a relative offset from the base pointer; global variables with a heap address; and heap objects that are identified by their range. And then we compare the destination that you got from the trap with the address that you get from here, and we raise alarm if there is no match. Now notice that for local variables and global variables, the addresses in this table are fixed. They can be initialized by the compiler. However, for heap objects, we need to be able to allow mallocs and frees to manipulate the data there. So we assume there is a trusted malloc call, which is also protected with our technique, and the trusted malloc is allowed to write to this table containing heap data. You had a question?
Can you explain a little bit why do you choose the 2 level of tracking? I mean,
Sure.
when the hardware level, of course, it's hard to achieve in practice, right?
Well,
that's the part, right? We don't have it in current CPU.
Well, okay, let me address the second question in a minute. But first, let me address your first question, which is why we have this 2 levels of checking. So first is we want to use hardware to do the slow operation in terms of checking which instruction is trusted or not. It needs to be done for every instruction. And then sort of filter out easily the ones that we need to do the more complicated checking for. And hardware, if you look at the rules for trust propagation, those are really simple. So you can build hardware to propagate that pretty efficiently, as I will show in our results. Now, for software checking, we are really going through this whole algorithm and checking multiple instruction ranges, etc. Now, in theory, we could design a efficient hardware to do that. But as I will show, the overhead of this software checking is actually very small compared to the overhead of compared to the overall overhead of the application. So that's why we chose to do the more complex check in software, but we do the sort of easier one, but that needs to be done on every instruction in hardware. Now, let me address your second question actually at the end, because you're asking about how practical this approach is. But I'll just say this: we are adding one bit for every instruction and data operand in our system, and I don't think. I mean, the hardware changes are actually pretty minimal, though it can go into that later. Yeah.
Is it possible to leverage work on putting bits in the hardware for taintedness.
Thank
in
you.
some way,
That's a great point. So there has been a lot of work like Raksha and the Chen et al. Publishers. So they associate a tainted bit with every item and then track it as it moves through. So definitely we can leverage those techniques. And in fact, we even explored using our technique as a policy to one of those other taintedness tracking techniques. But since you bring up the notion of taintedness, there is a difference in the sense taintedness can have false positives because user data may be allowed to write to these variables, whereas our technique doesn't have any false positives, at least for correct C code. So if you give us the code and user data can legitimately go and influence some data, and that's something that's there in the code, we will actually faithfully enforce that. So we are more like what shall I say? We enforce the source level properties of the critical data. Okay, so let me sort of tie these in together with the OpenSSH example, then I'll present the result. So this is the same example that I showed you at the beginning of this technique. So you have the authenticated critical variable. Now the compiler marks the instructions in the backward slice. So these would actually be PC program counter addresses, but for convenience I've just shown them as program statements. Right? It would mark the instructions in the backward slice as trusted instructions. It would also mark the instructions at the top as trusted data. Now, due to space constraints on the slide, I've shown the instructions that are passed into the function as trusted data. But in reality, this would be an interprocedural slice. And notice that the sprintf, which is the format string attack, and another instruction are actually marked untrusted. Now, rather than go through this, as I told you, we isolate the targets of each trusted instruction. And at runtime, using the rules for trustedness propagation, you would actually propagate the trusted bit to all these targets, all the way down to authenticator. So you see, you build up this whole chain of trust. Now, let's assume, I've just removed a portion of the graph to show you something now. So let's assume there was an untrusted instruction that came and tried to write to this shadow PW variable. So in the process, it's trying to manipulate it to its advantage and authenticate to the attacker. So when an untrusted instruction writes to this variable, it's going to clear the trustedness bit of that variable. Now, according to the rules of level 1 check, when I actually read from untrusted data, when trusted instruction reads from untrusted data, that's a no-no. So you raise an alarm and you prevent it in hardware. Now let's say you have a slightly smarter attacker or a different module which is going to, it's still trusted, but it's supposed to be writing to some other data. But you have somehow manipulated it through user input to go and try to write to this PW variable. Now this would be passed by the level 1 check, but it would be prevented by the level 2 check, because this would not be the allowed target for this variable. Now at this point, I should mention that whatever guarantees we enforce are only as good or as determined by the compiler's point analysis. So we need pretty precise compiler's point analysis for this module in order to make sure the guarantees are tight. Okay? So we tried this, or we applied this technique to 3 real server programs. So OpenSSH, WFTP, and null HTTP. Now in each of these programs, we protected a specific module that was important for security critical functionality. So in OpenSSH, we protected the authentication module because you don't want an attacker to misauthenticate themselves. In FTP, we protected the logging module. So whenever an attacker does whenever a user does some action, the action is logged. So an attacker may try to attack this module and erase their traces essentially. And the null HTTP program, we actually protected the web page serving module. So when you request a web page, it goes and gets a file which is distributed to you. So as an attacker, you can try to mess with that file and serve your own web pages perhaps. So in each of these, we identified critical variables based on our understanding of the code, which are places where the attacker would want to go and try to, which are variables the attacker would try to corrupt in order to get their ends met. And we found that we could, by protecting these variables, we had only, so we had only a few trusted instructions for each of these variables. So even if the rest of the code was still unprotected, you would still make sure that these variables were being protected in this module. And as you can see, the total number of instructions in each of these programs is pretty large, but the modules themselves are pretty self-contained, and the trusted instructions are even fewer. So the assumption here is that by protecting a small portion of this whole data, you can make sure that the attacker doesn't manage to violate any of the functionality you want to protect. And we have implemented this in the impact compiler, or the open impact compiler, using static analysis for extracting the information flow signature. The level 1 check, we have actually implemented it on a real processor, the Leon 3 processor from Geisler Research. And we had to make small modifications to the pipeline stages, but they could be mostly done in parallel with the pipeline, the operations, I mean. And then we actually went and synthesized this on an FPGA with Xilinx Vertex 2 Pro. So this was done by my colleague who modified the Verilog model with the rules that I had come up with. And then we found that the performance overhead for this technique, when you do level 1 check in hardware, is 10%. Now, for those of you who may not be familiar with hardware, 10% may seem like a large number. Where are we seeing this from? So it turns out that whenever you add a wire to your processor or any signal, you're going to have to slow down the clock because you're not going to be able to clock it at the same rate as before. There are longer wire delays. So we actually saw that when we added some of our structures, we were seeing this 10% increase in clock cycle time. And let me remind you that this overhead we would not have seen in simulation. In fact, we did a Valgrind-based simulation initially, and our overheads were almost 0%. But so whenever you see techniques, I mean, simulation is a great tool. I believe it's great for prototyping. But whenever you see techniques that report very low overheads, security techniques especially that report very low hardware overheads in simulation, you need to ask, what would this really be in the context of a processor?
So let me see if I understand the configuration. So the Leon 3, what is that?
So that's a Spark ISA. So what we do is we compile to the Leon 3 backend with our modifications. So we actually make our modifications off the so we pull out wires from the pipeline stages, and then we configure our checks in a checking module. That's part of the. So I didn't present the hardware architecture here, but I'd be happy to.
It's real hardware.
It's real hardware. It's executing.
Does the FPGA run slower than the main processor?
So that's a good point. So we actually synthesize this at the highest frequency available for the Leon processor. So, I mean, of course, we don't have access to a fab, otherwise, but I mean, from an academic project point of view, this was probably the best we could do in terms of trying to build this.
How you change the processor.
Right.
And I suppose you change it by having 33 bits.
Well, actually, what we do is we pull out wires from the pipeline stages. So we have a shadow register file for the register file. So we don't actually add it to the main register file. We keep everything shadowed, and then when you do a page fault, we bring in a bit mask for the trusted instructions in the page. So we try not to change the existing memory layout and the register layout in the processor. I can discuss the details, but that's more like an implementation.
That's not right.
I'm sorry?
The 10% doesn't sound right. And if you're using the same thing that the Stanford kids use, like
right.
use half of the memory for the 33 bits.
Mm-hmm.
And that's where the 10% goes.
Well, okay. I mean, we can probably talk more about this offline, but our synthesis frequencies you're talking about Raksha, right? So our synthesis frequencies are actually much higher than theirs. So we synthesize at the recommended clock speed. So that could be a reason why we are seeing these extra clock cycles. All right. So, and then we implemented the level 2 as a software library, and we found that the performance overhead was pretty negligible because, as you saw, the trusted instructions were only a small fraction of the overall program code. So, in summary, for the IFS technique alone, yeah, sorry. Yeah.
When you say 1%, that really depends on how many critical variables you are tracking, right? And in your test case, it's 1 or 2 variables you are tracking, and that's the 1%.
So that's right. So what we do is we go to the code and look at the variables that we think an attacker could exploit. Now, I'm not saying that the 1% is sort of the standard there. So if you protect more data, you're going to see an increase in that. But at least it's configurable based on how much data you want to protect in your application. So you decide how much price you want to pay and then protect it accordingly. Now, the 10%, however, is the fixed cost that you pay because of the extra hardware that you need to allow you to do this kind of configuration.
Yeah, but if you track 10 critical variables, do you expect that 1% become 5, 2, or 10?
So for these modules, they actually are the authentication module, logging module, are actually occupying like about 2 or 3% of the whole program execution time. So they're not on the performance critical path in this case. Now, and I believe that for many programs, the really security critical or reliability critical functionality is not going to be necessarily on the performance limiting path. Now, when I talk about Samurai, I'll actually show you an example where our assumption was wrong. We actually found a certain case where it was on the performance critical path, but I'll come to that later. Thanks. Okay, so the IFS technique ensures that critical variables are not compromised by memory corruption attacks. The security critical variables are identified by the programmer, and the IFS is extracted automatically using the impact compiler. And we have implemented this as a two-level checking scheme using hardware and software. And in terms of implementation, we have an FPGA hardware, a real processor that we synthesized on an FPGA, and we have various server applications that we tried on this. The performance overhead we observed in hardware was about 10%, and the software overhead that we observed for the applications and critical variables that we protected was negligible. So before I move on to the next project here, let me sort of give you a big picture slide on the other aspects of what I've been doing. So I've built this compiler framework for security and reliability, and the common aspects in this framework are as follows. So first, we identify the critical variables or memory objects and their locations in the program. Then from this, using static analysis, we extract the backward slices or the backward dependencies of the critical variables. And finally, we convert the backward slices to runtime checks to ensure the integrity of the critical data. So what I showed you was one half of the story, which is the security side, where you choose variables that are important for application integrity and then generate checks to verify that the value was produced by legitimate instructions. The other half of my dissertation actually deals with the reliability side of things, where you choose the variables that are important for application recovery, but you generate correctness checks for these values by actually recomputing them using the slices. So there we recompute, we come up with concise checking expressions for these critical variables and use FPGA hardware to recompute them as the application executes. I'm not going to talk about that today, but I'd be happy to take questions after the talk. So let me now move on to the second project that I'm going to talk about. This is Samurai, or critical memory, for reliability or protection from memory corruption errors. And this is joint work with Ben Zahn and Vinod Grover. And I started this work when I was an intern here, but continued it after I went back to Illinois. So the idea behind critical memory is as follows. So we want an abstract model, a memory model, for reasoning about critical data. So you want to be able to protect your critical data as well as be able to reason about it, so that you can you get some guarantees in terms of what protection you get. So the key here is that you need to mark the critical data using this keyword similar to a constant qualifier, and the programmer or the compiler has to identify where this critical data is read from as well as written to. So when you read from it, we use a special operation called a critical load, and when you write to it, we use a special operation called a critical store. So let me sort of give you a one-slide tutorial on what this memory model is going to do. Then I'll show you how we really use it. So as the critical memory, so essentially the idea here is that you slip a layer under normal memory. Okay, so you have normal memory on top, and underneath you have critical memory. Do you have a question? I'm sorry. Okay. Yeah. So this layer parallels normal memory and has special operations. So let's start with the critical store operation, which is cstore, which is storing the value 5 to x. So normal memory is shown in green and critical memory is shown in blue. So the critical store is going to update both the normal memory as well as the critical memory locations. Then you have a regular store. These are unmodified stores in a program, and they are going to write to normal memory as before, but they don't change the critical values. So at this point, when you do a store, you have x equals 2 and in normal memory and x equals 5 in critical memory. Then when you try to do a normal load, you're simply going to read the value in normal memory. So you're going to read the value 2, but you're not going to see the value in critical memory. Finally, you do a critical load. At this point, you're going to go to the value in critical memory and return 5. but you have a choice. You notice there's a discrepancy between the value in normal memory and critical memory, and you can either correct this discrepancy, as we will do, but you can also think of having a debugging model where you trap on this mismatch. Or alternatively, you can just ignore normal memory and say it's not my problem, I have my data anyway. So, okay, that was all about memory models. How is this really going to help me protect from memory errors? So let's say that this is the same code that I showed you 2 slides ago, the critical imbalance. And let's say there is a memory error here where you're going to try to write to buffer of 15. You're going to increment it by 200. Now, because of the way the compiler has laid out objects here, buffer of 15 is actually going to point to balance, assume this. So now when I try to, so let's see let me walk you through the steps here and show you what happens to the data. So when you see the critical imbalance, that gets translated to this map critical command, map critical instruction, which is going to make sure that your balance has a copy in normal memory as well as in critical memory. When you see balance equal to 100, this is, the compiler can recognize that this is just an update to balance. So it's going to it's going to use a critical store instruction to write to the value of balance, and it's going to update the value in both normal memory and critical memory with 100. Now, let's say you try to do a load. So this is when you do buffer of 15 plus equals 200. So at this point, the compiler is going to assume that all objects are infinitely far apart in memory, so it doesn't reason about memory buffer overflows. So it's going to translate the reference to buffer of 15 to a regular load instruction, and it's going to return 100. And more importantly, it's going to translate the store there to a regular store, which is going to actually increment the value in normal memory by 200. So you see at this point, you have a discrepancy between the value in critical memory and the value in normal memory. Now, you go back to this load here when you do balance less than min. Again, this is a load from a critical data location, so it gets translated to critical load. And in the semantics that we have implemented, we actually notice this discrepancy and correct it. So a couple of things to take away from this slide. So you see, you can actually selectively protect the data, critical data from memory errors, because from the point of view of this piece of code, it's seeing a consistent value. Yes, you have a question.
Compiler know to generate when the target of the assignment is the 15th element of buffer. How do you know to use the address of balance?
Right. So thanks. So what we do here in this example is that when you look at the compiler's static analysis, buffer of 15 and buffer and balance are 2 distinct objects, right? So buffer in this case is not critical. So it's going to, so whenever you have a reference critical data, it's going to generate critical loads and critical stores. For normal data, it's just going to be normal loads and stores. Now that being said, we haven't actually implemented a static analysis based system to annotate this. So for now, in the implementation I'll describe, we actually manually annotate it. So but you can think of having compiler support where when you reference critical data, you automatically generate critical loads and critical stores.
Right, I'm fine with that. I don't understand how you do that. Why doesn't it say temp was assigned load of ampersand buffer, and then do an indirect store with 15 elements past that?
Oh, so it could do 15 elements past that, but it would still be a normal store, because it doesn't know that store is in fact to critical memory.
You mean to say that just it happens to be balanced?
It happens to be balanced in this
So you
case.
don't mean to say the compiler recognizes the buffer plus 15 is balanced?
Exactly right. Yeah. Sorry, I should have said that. Yeah. So in this case, the way the runtime places the objects is in this fashion. But of course, from the compiler's point of view, these are all separate objects. Okay. Thanks. Yeah.
But what if like one instruction in the source code, I mean one line in the source code that you cannot decide during static analysis, it will be a critical store or it's a normal store? How do you handle that?
Right. So there are 2 ways to handle that. So first is if your pointer analysis comes back and says, I don't know where this thing is going to write. So you can give a warning to the user at that point and to the developer, and then you can try to make them, so when you try to use void stars, this is when this is likely to happen. So you can sort of use annotations to guide the compiler at that point. but you only need to do this for the critical data. The other way to think about it is you can conservatively mark stores as critical. As long as you're not doing too many of them, you're still okay, because critical stores can write to normal data just fine. It's just that the other, you don't want the other way, you don't want it to go the other way. So being conservative is an option, but if you really wanted to get the guarantees, then you would have to have precise analysis at that point. Yeah.
It seems backwards. It seems like if you can't tell, you need to call the normal operation so that, because otherwise the critical ones are allowed to write to these special parts of normal.
So it's an implementation choice. I agree. So you could have such a implementation where if you can't tell, you simply do normal stuff. But then at runtime, you're going to see a discrepancy between the value in normal memory and critical memory. So you may proactively correct it when that was not the intended effect in the code. So so it depends on which side you want to err, whether you want to err on the side of caution, whether you want to err on the side of, it doesn't matter if occasionally you miss a write. But I believe it's better to err on the side of caution here and give a message to the programmer saying, look, I can't really tell where you're writing to. Can you make your intentions more explicit?
But what can you add a runtime check to do?
Right. So the runtime check here is only going to tell whether you're going to write to critical data or not, right? Because you get the destination and then it's going to tell at runtime whether it is writing to critical data or not. You still don't know statically where it was going to write to. Because you don't know if it was allowed to write to critical data or whether it was not. So here's the way to think about it. You get an address at runtime, right? So if it happens to be a critical address, right, and it's a critical, if it happens to be a critical address, you don't know at that point whether the store there was in fact supposed to write to that critical address or not. Right, but we don't know whether the store instruction was a critical store, right? Because if you don't mark it, if you just marked it as a normal store, then you reason that it's not supposed to write to the critical data.
How about you just you either create a assert store instruction or you just check if else, right?
Yeah, the if else works. In fact, we do the if else, which is why you can conservatively mark stores as critical in your code. So you can mark a store that never writes to critical memory as critical, and you'll be fine. Our program still works. The problem comes when you miss stores that were going to write to critical memory, but you forgot to mark them. I don't know if I'm being clear.
I'll talk to you.
Okay, yeah, but I'd be happy to go over this. Yeah.
I feel like I missed something. Why bother, if you have this critical balance, why bother storing it in normal memory at all?
Okay, so I have not told you so far about the actual layout of memory, but one of our assumptions is that as far as possible, you don't want to change the format of pointers to memory, etc. So you want this critical balance to be sort of manipulated in the regular program using a regular pointer. Now you can think of storing this in, say, a separate address space, for example, and it's certainly possible, but that's an implementation choice. At this point, all I'm saying is critical memory gives you this notion of separation between critical data and normal memory, and allows you to reason about it. When I come to Samurai, which is the implementation of this, I'll actually use replication to store multiple copies of balance. So you don't need to go to a separate address space. In the same address space, you store it in different scattered locations. And then you do a majority voting to make sure that the value of balance is not corrupted. Okay. Thanks. All right. So now there's one more question here. What happens if what happens when you had untrusted third-party modules? So let's consider the same code as before. So you had a buffer and you had this update of balance. Let's say at this point you call this function which is untrusted, and you don't have the code of this function, but you're going to call it with x and y. Now, in the untrusted function, it's going to read the value of balance, and it's also going to do an update of balance, let's say. So it's the same case as before. Now you have a discrepancy between the value in normal memory and critical memory when this function returns. At this point, you as an implementer of the caller code has a choice. You can say, I don't trust that guy to mess with my value of balance. So I'm simply going to ignore him and go ahead with my computation. So you don't have to do anything at this point, and your value of balance is preserved. But what if you actually sort of trusted that code to update balance, as long as it didn't write some outrageous value in there, let's say. So at this point, you can check the value of balance in the caller function, and then you can do an explicit promote operation, by which you're saying, look, I trust this code to update balance because I have just checked that they did what they were going to do. So now I'm going to copy the value of balance from normal memory to critical memory. Now note a couple of things again here is that if this function, let's say, crashes or doesn't return, you're fine because the critical data is still correct. Or if it messed up the value of balance, it's fine because you're going to check it. Also, the function is only allowed, so only the modifications made to balance are actually promoted. So if it corrupted something else, like say your password here, you don't promote it, and hence the corruption simply disappears. So from the point of view of this code, you can almost walk through this and reason about what gets changed where. So this is the local reasoning aspect that I alluded to that you get from using this model. So far I've told you all this nice memory model where you have this hidden layer, right, and then you have special instructions. And it may seem like what I've been describing is a hardware implementation, but actually we can implement this in software, and this is what we did, which is in the case of Samurai. So we built a memory manager to protect critical heap data in applications. And here the insight is as follows. So when you have an object in memory, we are going to keep two replicas of that object that are randomly scattered through memory. Okay? And they are going to reflect the contents of this object at any point. Now also we keep pointers to these replicas in the metadata of the main object. So now when you do a critical store, it's going to go and update all the three replicas by following these metadata pointers, and it's going to make sure that the changes are reflected. Now let's say you did a regular store operation. At this point, this is your memory error. So you could overwrite any of these replicas. Here I've shown you overwriting the main object, but it could be any of these replicas. But when you do a critical load, you're going to do a majority vote of these three replicas. At that point, you'll notice the inconsistency, and you can optionally go and repair. And in fact, we repair on this mismatch. So you may be wondering what happens if this metadata is corrupted, because this pointer is a stray one. You can write wherever it wants. So we also take care to protect the metadata with checksums and store it in a special backup mechanism. So the way to think about it in terms of critical memory is the critical memory state is got by the majority of the state of the replicas. Okay. And I won't go into the implementation details of Samurai here, but if you have questions, I'd be happy to answer them.
Two applications.
Thank you. So so when we talk about critical memory, we had just one copy, right? And we assumed that somehow you couldn't write to that. Now, when you talk about the heap as a whole, pointers are writing wherever they want, right? Essentially, so we can't really be assured that one of the other copy that we had in critical memory doesn't get corrupted. So we actually split it into two, and so that we can take the majority of three to get the state. So we don't have any guarantees about what gets corrupted and what doesn't. So we have to have three in order to be able to detect the corruption. Did I answer the question? Yes. All right. So to evaluate Samurai, we have an automated Phoenix pass to instrument loads and stores in the code, and also a runtime library for allocation and deallocation of critical data. We protected critical data and applications mostly from the spec suite of programs. We chose data that is crucial for recovery from program failures. And we evaluated the performance by instrumenting loads and stores. And we also evaluated how dependable this is by actually performing fault injection experiments. In order to explore its utility even further, we protected critical data in libraries. Like we took a memory allocator where we protected the heap metadata, and we took an STL list class where we protected the backbone of the list structure. And I'm going to show you the results for these. So the performance overhead with Samurai, we chose 5 applications. I won't go into how we chose the critical data here, but if you have questions, by all means ask me. So you see that, so the yellow golden bar is the baseline and the blue bar is Samurai. So you see the slowdown for 4 of our 5 applications is within 10%, which is good. But the bad news is that for this application, gzip, our overhead was almost as 3x. And this is the question that you asked earlier. What if you actually chose critical data that was being intensely used? So that's what happened here, where in gzip, we protected the Hoffman decompression tables. because we figured if there was an error in them, you were going to mess up the whole downstream decompression. So it turns out that those are precisely on the most performance critical element in gzip. There's even an FAQ out there that shows you how to optimize the number of bits in these tables to get efficiency. So you need to be careful about what critical data you want to choose, because otherwise you could end up in something like gzip. This was the lesson we learned, at least. So, but the encouraging news here is there are applications out there like these 4 where you can protect a small amount of data and with reasonable overhead. So just to make this concrete, so in BPR we protected the routing data structures, Crafty we protected the chessboard, in parser we protected the dictionary, and in rayshade we protected the scene of objects. But I can go into why we chose that later. Yes.
But gzip, if you remove you currently maintain 2 replicas. If you only maintain 1 replica for gzip, would you reduce performance overhead?
So that's a good point. We haven't explored, reducing the number of replicas here, but the most So here's the real thing. The overhead comes because of the extra metadata lookups in the objects and then going to the replicas. So it's not so much the actual loads or stores among the replicas. Now we do have an optimization of Samurai where we check only one of where we compare the replica with one and then go to the third one only when there's a mismatch. But but you need to be careful there, because if you don't ever check the other one, then you let it accumulate errors over time. So we periodically swap pointers. Actually, there's a lot of implementation tricks that I'm not really talking about here. But yeah, that is one trick we can play to actually reduce the overhead of loads. So let me present to you the memory allocator results. These are interesting. So here what we did is we took a standard Kingsley allocator and we protected the heap metadata that is stored by this allocator. So as many of you know, there are security attacks that just focus on attacking the heap metadata and try to take away a system. So the real insight here is that only your allocator should be able to write to the metadata. The application has no business going and trying to write to the heap metadata. So in this sense, the application becomes the untrusted third-party code, and your allocator is the trusted entity. So we actually instrumented the fields of the heap metadata and compared it across a bunch of heap-intensive applications, memory allocation-intensive applications. And we found that our average performance overhead here was 10%. And the worst case is 20, as you can see. So to give some perspective to this number, there are papers out there that actually recommend separating the heap metadata into a separate process, because they're so worried about it being corrupted. And even with a whole lot of implementation tricks, their overheads are 50% or more. And whereas by actually being selective and protecting the heap metadata in the same space as the object, our overhead is only about 10%. And I will go over this quickly. We also protected the STL class, where we protected the backbone. We had to make some changes to the various functions, but these are like one-time investments. You make these changes. And after that, we used this STL class in a web server for maintaining information about incoming connections for clients. This is a multi-threaded web server. And we actually evaluated this across multiple threads and connections. And we found that the maximum performance overhead was 9% here. Before I sort of move Samurai, let me give you our fault injection results. That is one part of this. So this is our this is for one application, which is VPR. So what we did was we corrupted heap objects with some periodic rate, critical heap data, and we measured how often the application fails versus how often it succeeds. The graph on the right on this side shows the results without Samurai, and on the left it shows the results with Samurai. And the golden bars are successes. Yeah, we actually finished. And the failures are the blue bars, which are, the application crashed or went into an infinite loop. And so we see, first of all, you see that you have a lot more gold with Samurai than without. Okay, so that's good news. I should have said this earlier. The x-axis is how frequently we inject a fault. So when I say 100,000 is a fault period, that means every 100,000 memory access, I went and corrupted a heap object, a critical heap object. So there is, however, this one little red bar at the top, where at a very aggressive fault rate, Samurai actually detected something was wrong, but it wasn't able to corrupt it. because both our replicas actually managed to get corrupted by the same error, by two different errors, I'm sorry. Now, this problem could have been avoided if we had more replicas and paid more overhead, of course. But this just shows that even though there are cases where Samurai may not be able to correct your error, at least it detects it. And this is only happening at really aggressive rates. So we also did injections into non-critical data to measure error propagation. I'm not going to present those results today, but I can talk about them offline. So in summary, I presented Samurai critical memory. Critical memory is your memory model. It's an abstract model to reason about critical data and applications. We have special operations called critical loads and stores, and we allow them to interoperate with untrusted third-party code. Samurai is the software prototype of critical memory. It uses replication and forward error correction, and we have demonstrated it on both applications and libraries and found overheads of 10% or less. I just want to say a couple of things here. Critical memory is an abstraction which can be implemented in many different ways. So we can even look at a hardware implementation of critical memory. And I spent the summer of 2007 here where I explored a hardware implementation of this with Oner, Mutlu, and Benzon. We are also currently looking at other kinds of software protection techniques. So other than replication and voting, can we do smarter tricks in software to ensure critical memory semantics? Yes.
You mean it just didn't call down, or it produced the correct results?
It produced the correct result. So I sort of coalesced three things in those blue bars: crashes, incorrect outputs, as well as hangs.
So your technique basically is mostly to prevent against attacks and not looking about power correctness and errors, programming errors.
So I'm talking about correctness with respect to the critical data. So if it completes correctly with respect to the critical data, that's all in that experiment. That's all I care about. Now I had another set of experiments that I don't put up here, where we looked at the overall correctness of the application as a whole. So and there we injected errors everywhere, not just in the critical data. And we wanted to see how often it was the case our critical data was not corrupted by those errors. But I didn't put those numbers up. Thanks. All right. Let me now sort of briefly touch upon future work, and then I'll conclude. So there are three directions that I would like to explore, starting from this critical data paradigm. So first, and some of you actually pointed this out, that you protect some data in your application. But how do you know that's enough from a formal point of view? So can we do better? And I've given you various experimental as well as anecdotal evidence, but I've not so far actually given you a formal foundation to believe that the critical data is the one you want to protect. So what I would like to explore is, given a source program and specification, can we actually identify the critical data automatically? So with respect to the specification, can I figure out which data needs to be protected, and then implement those checks on critical data, and then pass this through a compiler to protect your program. Now, you can do better. How do we know, in fact, that this protection is sufficient? Because both errors and attacks are going to happen at the program on that level. So here's where I believe we can leverage formal techniques. So you can use a model checker to take a set of errors or attacks and then systematically explore the space of those errors on the program protected with the checks, and then see if that's enough. So you can get one of two things. You can say, yeah, the program is correct, or you can say, sorry, here's a counterexample. And you can go back and close the feedback loop with a counterexample. So I've actually already built the model checker for looking at errors as part of my PhD thesis, and this is the work. So this looks at hardware errors. This is the work I alluded to earlier. I'm trying to extend that to security attacks, and but I haven't even come close to looking at how to close the feedback loop and look at this. So that's something I would like to explore as part of future work. So the other direction I would like to explore is this notion of secure compilation. So as I was saying earlier, in the IFS technique and even in Samurai, a lot of the guarantees you get from the technique depend on the efficacy of the compiler analysis, the accuracy of the pointer analysis. So we actually came up with qualitative examples of which pointer analysis work better to guide our choices. But wouldn't it be nice to have like a quantitative model to actually choose the right kind of pointer analysis for a given level of protection? This is what I would like to explore. So for this, first we need to understand three things: what optimizations benefit security, what optimizations are detrimental to security, and other new optimizations that we can explore to protect this data selectively. And what makes this different from other pointer analysis approaches is that we can selectively tune the precision of the analysis for critical data and programs. Because remember, we want to protect this data, this critical data, so we can actually come up with efficient ways to track the pointers to that data more accurately. And the third direction that I would like to explore is using multi-core process to do checks. And multi-cores are here, and they're presumably here to stay. So how can we leverage them to get what we want? So given a program, I plan to use automated techniques to extract the critical data checks. The regular program is compiled on to a multi-core processor here, whereas the critical data checks are compiled on to a special purpose compiler, using a special purpose compiler to dedicated cores. And what I believe is that as the number of cores increases, you're not going to be able to leverage all of them necessarily to get the performance you want. So can we have a few dedicated cores for checking reliability and security? And since we are only considering critical data to be checked, we can actually share the dedicated cores among multiple main cores. So rather than go and use all the available cores for performance, can we dedicate a small amount for reliability and security and compile efficiently for those cores? This is a direction that I would like to explore and I'm pretty excited about. So in conclusion, I've shown you, or hope I've shown you, that critical data protection is a promising new approach for containing errors and attacks. And the idea here is that we will selectively protect a subset of application data, allow local reasoning for application modules, and also tune the cost of protection based on your application. But this is only one step in my broader research vision, which is to provide reliability and security to existing applications with as low overhead as possible. So there's a huge investment out there in C, C++ code, and we really have to come up with these kind of techniques to be able to protect them so that, and safeguard our investment in these applications. So for that, I believe there are two things that are necessary. One is we need an easy adoption path. So we need to be able to protect these applications incrementally and start seeing the benefits as and when we do the protection, not wait till we protect everything in order to see tangible results. And that brings me to the conclusion of my talk. Thank you all for your attention. I'm happy to take questions. And if you have any...
Can Samurai be robust for an attack that's aware that Samurai is existing in the system?
Yeah, so right now we do not design, we did not design Samurai to protect from intelligent attacker. In fact, I should have probably emphasized this more. Samurai was designed more for accidental protection, accidental memory errors. We have been exploring, however, ways to make it more robust to attackers. So, for example, we can hide the location of the critical data of the pointers to replicas, or we can encrypt them. Now,
if the attacker is not aware that Samurai is in the system, then it provides protection. Right?
It provides protection for the critical data from the attacker. If the attacker is just regular running the usual kind of attacks. Now, however, if you really wanted to protect against a smart attacker who's trying to game the system, then we would have to encrypt where we store the critical data. And the hope here is that the attacker, since the attacker can't go and figure out where these replicas is, he or she will not be able to corrupt them, and hence we can detect it. And in fact, this is one direction that we are exploring as part of this integrated framework for configuring the level of protection depending on our needs. And this is ongoing work with Benzon.
It's not enough to break the direction, but you have to also break the copy because you can search the entire memory to look for the copy.
Right, that's a good point. So it depends on how much power the attacker has. So if you're thinking of an attacker who sort of freezes the application, takes a snapshot, and then searches and then uses various cryptographic or entropy measures to look for this data, you're right. I mean, we won't be able to protect it. So there is there's different levels of protection from an attacker. But if you really wanted to protect against a smart or a Uber attacker, then I would recommend you use IFS, because now even with Samurai, an attacker can change the dependencies, right, or where the critical data is derived from and get in the system. Whereas with IFS, we encode the whole backward dependence tree. So we already have a way to protect from Uber attackers. So Question is, with just software support, how much closer can we get to where we want to be? Thank you.
But you said like this tool works focus on protecting critical data, but on the other hand, we have facing control flow attacks, and you have done like in your first work you have this level 1, level 2 protection. But the thing is, can you leverage what you are proposing for protecting critical data for protecting control flow attacks? Because otherwise, I need to pay two overhead to achieve a safe system and security, right?
Well, yeah. So as it stands now, our system is more focused for data protection. Now, there's no reason you couldn't use this for protecting control data, but you're going to pay that kind of overhead. Now, I would actually say there are other efficient techniques out there that do a fairly good job of protecting control data. So control flow integrity and program shepherding are two such techniques. So after you have employed the techniques like this and protected control data, what are your attackers going to do? They're going to come after these kind of variables in the program which are going to give them maximum benefit. And actually Chen et al. Shuo Chen here showed that such attacks are practical even for current day systems. So I would argue that to really leverage the benefits of our system, we go after the kinds of attacks that would be launched after you already have control data protection in place. But that being said, there's no reason you couldn't apply it. Just you're going to pay overhead.
Yeah, but I guess your current solution cannot be applied directly for that, right? You cannot just treat return address as a critical data because that's.
Well, you could, but that wouldn't be the most efficient way to use it. There are more efficient techniques out there. So, as I said, I'm not trying to compete with the control data integrity, control data checking techniques there, because I'm saying after we protect those, what is left for an attacker, and that's where my focus is. Thank you all.